by Claudia Polini from Notre Dame on core of monomial ideals. So Claudia, you are welcome to begin your seminar.
Thank you very much. Thank you, Jugal, and thank you to all of you to come to listen to me. So this is the second talk in the series, so I will refer to many results that I said on Tuesday. So this is mainly joint work with Ulrich and Vitulli and Fuli, Montagno, and Ulrich. So we start with a polynomial ring in D variable over an infinite field. And we take an ideal I inside this ring and we assume is a monomial ideal. So I'm going to write that here that is a monomial ideal. And A1, AN are just exponent vector. And we denote always with M the homogeneous maximal ideal of R generated by X1, XT. And we want to talk about the core. And since we want to talk about the core, like I talked last time, we need to consider reductions of I. And I remind you that reductions of I are ideal over which I is integral. On the other hand, you have their counterpart, which is the integral closure of I. And the integral closure is the unique largest ideal, which is integral over I. Now, even though I is a monomial ideal, I may not have any proper reduction that are monomial or even homogeneous. However, so you immediately, when you consider reduction, you go out of the realm of monomial ideal. However, I bar is monomial. And I bar is determined by what we call the Newton polyhedron of I, which also denote with NPI and is the set of B vectors in non-negative integer, I wanted to put a 0 here, but they're vector, you need D of them, such that B is bigger than equal than the sum of the CI, and when I use the exponent vector of my ideal, and then the CI are require the sum of the CI has to be 1, and the CI are non-negative rational numbers. And this, if you want, is the convex hull of the lattice points given by the monomial generators. And to this lattice point, you have to add actually the positive orthant. And that's how you get the Newton polyhedron. And what is I bar? I bar, once you have the Newton polyhedron, is very easy to describe. Is just all the monomial whose exponent vector are exactly the B, which are in the Newton polyhedron of I. So I bar has a beautiful description. It's generated by this ideal. And recall that there is another important ideal when you want to study the core, because if you go to the local case, and here we need to go to the local case, the Lippmann had proved the adjoint of I to the M to the L, and I remind you now what L is contained in the core of I. And again, core of I M, because I'm in the local case, and this is obviously in the integral closure, because the core is in I and is in every ideal. So let me remind you first what is L. L, the L that you take here, is the analytic spread of I localized at M, okay? You cannot really define the analytic spread in the global case, so I want to take that this L is the analytic spread of I localized at M, which is the minimal number of J for every J minimal reduction of I localized at M. is also, if you want, remember we talked about it last time, the dimension of the special fiber ring of I localized at M. Okay, and that we talked last time. Now, as we saw, this IM is a monomial ideal, but also the adjoint is a monomial ideal. Okay, actually, for any monomial ideal I, the adjoint of, let me still show the Newton polyhedron, the adjoint of I is monomial, determined by the interior of the Newton polyhedron. I'll denote it like this, the interior of the Newton polyhedron of I. And the adjoint of I, we can write it this way, is again generated by the monomial, okay, whose exponent vector has the property that B plus the unit vector 1 is inside the Newton polyhedron of I. And this was proved by Howell in characteristic 0 and then by Hubel and Swanson in positive characteristic. And this we are still talking about 2000, early 2000. And as an example, let me make an example of this situation, and then we try to come back to this example later to compute the core. Let's take the ideal x to the third, so x1 to the third, x1, x2, and x2 square. This is obviously a monomial ideal, very simple. Is actually, now we're going to make the Newton polyhedron. So let's try to make something decent here. And I have 1, 1, and then 2 here, and 2 here, and 3 here. Okay, not very well posed, but it's okay. Then I have the point. So this is the point x2 square. This corresponds to the lattice point x2 square. This corresponds to the point x1, x2. And this corresponds, let me do it in green. So these are the monomial in my ideal. And now the Newton polyhedron of I is simply this one. This is the Newton polyhedron of I. And P of I. So this shows already that there are no lattice points outside. So this shows that this ideal is actually integrally closed. Now, what about the adjoint? The adjoint of I, we can see immediately that actually is strictly, okay, bigger than I bar, because these 2 points are already in the adjoint. Because if you add 1, 1, they go to finish in the interior. So the adjoint is simply the maximal ideal in this case. So this should show what I talked about. And as I said, we'll come back to this example later when we compute the core. Notice that in this example, I does not have a monomial reduction generated by 2 elements. Actually doesn't have any proper monomial reduction. And now the core, I want to remind you that the core of I is the intersection of all reduction. Okay? And we could ask, so the core is sandwiched between these 2 monomial ideal, and we could ask, is the core monomial? And the answer is yes. And why is the core monomial? Because of the torus action. The torus action, you remember, fixed monomial ideal. And the torus action sends reduction to reduction. Hence, it fixes the core. Because since it fixes I, it sends a reduction of I to a reduction of I. And so it fixes, it just sends reduction and reduction. So it fixes the intersection. So we get that this guy is a monomial ideal. And so the question is, does the core have a nice interpretation? Or a nice in terms of monomial operation, and we'll try to answer this during the talk. We could even ask if the core have a nice combinatorial description in terms of the Newton polyhedron. And the second answer, the second question actually has a negative answer, because we know, and we talked about last time, that the core in general is not integrally closed. Even if you start from an integrally closed ideal, the core is generally not integrally closed. So obviously, if the core is integrally closed, then we have a hope, because what we hope is that if the core is integrally closed, actually we can still hope that the core is the adjoint. We talked about this last time, and this question, as Jugal wanted me to put as many open problems as possible in this talk, I would say is the main question still: when is the core of I equal the adjoint of I to the L? And I don't need to localize to ask this question, and I want to ask when is this true in general. Now, I want to cite some results towards this. Some are corollary, and some I already said last time a little bit. The first one is a corollary, because in the case of the monomial ideal, we have more hope to achieve this, and we still hope that it's going to be true when the core is integrally closed. So first of all, let me put this result that, as I said, is a corollary of what we did last time. This is work with Ulrich. So assume that I is monomial. This is the setting today. And the dimension of R mod I is 0. So I is an M primary ideal. And then we assume that I is asymptotically normal. So the power of I eventually are integrally closed. Then the core of I is indeed of I to the D. In this case, the analytic spread is D. Why is this true? Why does it follow from what I said last time? The point is that the projective spectrum of the Riesz algebra and the projective spectrum of the integral closure of the Riesz algebra are the same because of this condition. And now, remember that the condition to prove that the core was the adjoint was star, which is always satisfies because the dimension is 0, because it's an primary ideal, and also the fact that the projective spectrum of the Riesz ring had to have rational singularity. But since the projective spectrum of the Riesz ring is the same as the one of the integral closure of the Riesz ring, and the integral closure of the Riesz ring is a monomial normal ring by Oxter and Buteau, then we know that it has rational singularity. So this is the reason for which this follows. Now, another class of monomial ideal that we actually can compute the core, and the core does give us the adjoint, is, this is work with also Vitulli, is the case in which you consider a polynomial ring just in two variables, x1, x2, and you have the ideal I, which is simply, you can write it, this is without any condition, you can extract always a monomial, the monomial could be 1. And then what we really assume, that's a big condition, is that this ideal is a monomial ideal generated in the same degree. So you can always write it this way, since it's generated in the same degree, okay? And then you have, let's say, x1 to the ki and x2 to the n minus ki. So these are the generator of I. And so and when you take delta, okay, which is the GCD of n and the ki, and then the core of I is again C, x to the delta, x1 to the delta, x2 to the delta, and 2 times n over delta minus 1. So very, very simple shape. And in particular, if delta is 1 and C is 1, then the core is the core of m to the n, which is m to the 2n minus 1. which is also the adjoint of I squared. So this is another case where the core is the adjoint. I must say that actually this is generalized by work of Kasten, myself, and Ulrich. This kind of result works for not just for monomial ideal, but for any ideal generated by form of the same degree in a polynomial ring in two variable. And what we relate again, the core, we prove that the core has the same, a similar shape, is again the core of the maximal, of the power of the maximal ideal, if the map is birational, or if you want, if and only if the projected spectrum of the Riese algebra has a property R1 of Serre, which is also equivalent to the fact that the core is integrally closed. And also there we give a nice description, very similar to this one for the core of an ideal, just not assuming monomial, but in this case, I'm in the monomial case, so I wanna just state this. So now, you could ask, as I said before, like like in this case, the core, the I doesn't have to be integrally closed. I doesn't have to be even eventually normal, asymptotically normal, for the core to be the adjoint. Really here, the only thing that you need is that the core is integrally closed. So is this more true? And actually this was asked by Craig Uneke, whether for an ideal of dimension 0, it suffices for the core to be integrally closed, to be the adjoint. And this actually was answered partially by my student, Kohlhaas. She proved that if I is a monomial ideal such that the integral closure of I bar is the integral closure of this regular sequence. This means in particular that I is zero dimensional, and also that has a degenerated reduction, monomial, which usually is not the case, unfortunately. So this is, if you want, half of the cases, when the core of I is the adjoint of I to the D, if and only if the core of I is integrally closed, if and only if R the Riese algebra, or if you want the project of the Riese algebra as R1. And actually, to prove this, which is quite hard, she uses a symmetry on the core. I'm not going to talk so much about it. What I want to talk a little bit about is the fact that, you see, it's clearly needed, that this one, for having the core equal the adjoint. And we know already by work with Ulrich that if the core is, if the Riese ring has R1, then the core is integrally closed. So we know this implication, but it's interesting, why is this implication true? So that's the one I would like to just show you. So why is this implication true? Let's call it true implication. So really, why these two together, they give me that the Riese ring as R1. The reason is because the core, and that's, I think, is important to remind what the core really means, and the adjoint of I to the D, they both in this situation can be written in terms of a component of the canonical module. This is the D component of the canonical module of the Riese ring of Ri, and this is the D component of the canonical module of the integral closure. And the fact is, you always have an inclusion of canonical module. The canonical module of the integral closure is contained in the canonical module of RIT. And they are equal in, obviously, when you look at it in degree D, but actually they are also equal. Okay, let me write it this way. Yes. They're equal for every j bigger than equal than d. Why is this? This is because with Ulrich, we proved that in this situation, this canonical module is generated over RJT by element of degree strictly less than d. So if they are equal in degree D and the generator are all before, then they have to be equal for every J bigger than equal than D. And now what we do is dualize this picture into the canonical module. And if we dualize this picture, what we get is the S2ification. We get the S2ification of the Riesz ring, of the integral closure of the Riesz ring in one side, and S2ification of RIT in the other side, and they have to be equal. Why? Because the S2ification is S2, and since they are equal in large degree and obviously equal for negative degrees because they're just R, these two guys, you know, are the same, but this is the integral closure of RIT. So this forces this ring to be normal. But if it's normal, is R1 and S2. But you don't obtain the R1 property when you S2 The R1 property must have been in the ring already. So RIT is R1. Okay? So this is why RIT has to be R1. And the hope, as I said, and this is the open problem, one of the open problem I really would like to point out, is trying to prove this same result without this condition. We believe that this is true without that condition. Okay, so now I would like to go to the next chapter, and I would like to talk about the interpretation, the first question I asked, the interpretation of the core in terms of monomial operation. So I'm going to talk about the big mono and the small mono. So this is the next chapter if you want. I'll have 3 chapters here for this talk. This is the longest maybe. So let L now be any ideal in R, okay? R is still the polynomial ring in the variable over an infinite field. And I want to define the mono of L and the big mono of L. So the small mono of L is the largest monomial ideal contained in L. And instead, so this by definition, and this guy instead is the largest, again, sorry, the smallest, not the largest, the smallest monomial ideal containing L. Okay? So the mono of L, the big mono, is very easy to describe because it's the ideal generated by the monomial support of the generators of L. So it's easy to describe because you just collect all the monomial that appears in the generator of L and you take the ideal generated by it. The small mono, this ideal, is much harder to describe. However, there are algorithms even implemented already in Cocoa, and the mono of I can be computed using Cocoa, for example, from the command which is called mons in ideal. I should still call it L since I call it L of L. Okay? Now, I would like to talk about an algorithm that is important to compute actually the mono, which I think is the algorithm behind monovel, which is the algorithm of Saito, Strunfeld, Takayama. And when I say mono, I always mean the small mono. If I talk about this guy, I'll say the large mono, because the small mono is the most important. That's why I'll always call it a mono. So now, how do you, this algorithm says, first of all, you have to form the multi-homogenization So mono L here, not mono I, mono L. So you call it LH, and to get the multimodalization, you have to add D variables, one for each of the xi. Okay, I'll tell you more how you do that. And then after, the second step is to contract back to R. So the mono L is simply the intersection of this multi-homogenization with the ring R back, okay? Because we have extended this variable. So how do you do this multi-homogenization in general? If you have an element, let's call f x1 to the third plus 3x1 x2 minus x2 square, then the multi-homogenization is done this way. You have to think about, remember, because this is a monomial idea, you can give a multi-degree, and let's say x1 has degree 1, 0, and x2 has degree 0, 1. So this would have degree 3, 0, this element, and this element would have degree 0, 2. You want it to be each term multi-homogeneous, so you give to the UIs the same degree as multi-degree as the xi. So here, to be multi-homogeneous with this, you need a 0, 2. So I have to multiply this term by u2 square. So what I get is fh, the multi-homogenization, is simply x1 third u2 square plus 3x1 x2 u1. Here I need 2 of the x1, so I put 2 of the u1 and 1 of the u2. And here I need instead all the x1, but it's not x1, so I put a u1 to the third. And now I get that every term has the same multi-degree. How do you get the multi-homogenization of the whole ideal? In theory, you have to multi-homogenize every element of the ideal, but it's much easier. You can just multi-homogenize the generator and then saturate respect to a product of the UI, and that will be enough. So that's what you have to do. And this is the algorithm. But we give with Vitulli and Ulrich, we give a much easier algorithm to compute the mono. A much easier algorithm that uses linkage has only the problem that it works for a primary ideal, for ideal that have dimension 0. So assume that L is dimension 0 is actually is in primary, not just dimension 0. I want to assume that L is in primary. And then I consider alpha, which is a regular sequence a monomial inside L. I can always find such L because L is in primary, such alpha because L is in primary. So this condition gives me the presence of this regular sequence inside L. And then notice also, because it's going to be important, this is just a notice, that this alpha is actually contained in the mono of L. This is true because, why? Because alpha is a monomial ideal and is contained in L. But every monomial ideal in L is contained in the mono, because the mono is the largest monomial ideal contained in L. Okay, now our assertion is that the mono of L is simply alpha colon the big mono of alpha colon L. And this really use linkage. And now I'm going to show how this works. Okay, remember the colon is simply tells you all the element of R that send one ideal into the other. So let me do this inclusion first. So you start with alpha colon L, which is the ideal here in here. And you notice that I can make this ideal larger if I take a smaller ideal here. So I'm going to take a smaller ideal and I'll take the mono, which is smaller. Okay? And then, because these two are both monomial, this column is a monomial ideal, because column of monomial ideal is monomial. Is a monomial ideal, and now notice that contains alpha colon L, so it has to contain, contain the big mono, because the big mono is the, remember, is the smallest monomial ideal that contains it. So it contains the big mono of alpha colon mono L. Good. And now we are done. We can reverse the inclusion using linkage. If you take the column with alpha again, so you take alpha, the column with alpha again, alpha colon, and that's all you do. The mono, sorry. So you reverse this inclusion. You want to reverse this inclusion, okay? And you take alpha mono alpha colon L, okay? And this inclusion will become this, and then you have alpha colon mono L. And now I use what I told you before, that alpha is contained in the mono. Because of this becomes simply the mono of L. And I'm done. So now we have prove one of the inclusion. The other follows more or less the same way. You use the same ideas. You start with L, which is alpha colon alpha L, because alpha is contained in L, and then you make this ideal smaller by taking a larger ideal here. So taking the big mono, and now we have alpha colon mono alpha colon L, and again the same trick. This is monomial, so this is monomial, but this is a monomial ideal which is contained in L, so it has to be contained in the mono of L, as I told you before. And the proof is finished, because we wanted to prove that this is contained in mono L. So this really gives us an algorithm. But how is the core related to this mono, to this idea? So let me now go back to I being a monomial ideal, as I always wanted. In fact, this I indicated with L because it was no monomial. Okay, I is a monomial ideal, and I'm asking this question. How is the core related to the mono? So first of all, let me notice that if I take J, any reduction of I always have, obviously by definition, that the core of I is contained in J. But the core is a monomial ideal, so the core must be contained in the mono of J. Okay? So we always have this containment. And the question is, when is this inequality? And the point is, it will not be in general, because if I has a proper reduction, which is monomial, then when you take the mono, you get the reduction back, and that will be too large to be the core. However, if you take an ideal which is very far from being monomial, a reduction which is very far from being monomial, then you hope that the mono becomes smaller, and then it becomes the core. So, but the best ideal to act, best reduction to take, we talked about this last time, we emphasized this last time, a really general reduction, because otherwise you wouldn't know how to choose it. So now assume that L is D. Remember, this is always satisfied if I is zero dimensional, but I don't want to just do the zero dimensional case. And now J, let's define, this is got as an important definition. I take D general, K linear combinations of the monomial generators of I. If you are in the local case, this would be what we call last time a general reduction of I. So what's happened, and it would be obviously monomial. So what happened if I localize, this is a general minimal reduction of I localized M. However, in the global case, J itself may not even be a reduction of I because it could have different minimal prime. So we have to consider another ideal, and the ideal we consider, we call it K. These are very important, are the guy that will come always on now, from now on. And this case, just J, but when you throw in an element of I to the D. So you take any element of I which is different from 0 to the power D, this is the dimension of our ring, and then this K turns out to be a reduction. A reduction of I, not only a reduction, but also with the property that locally is indeed a general minimal reduction of I by Brianson-Skoda, because this F to the D is contained in every reduction. So we call this K is called from now on general reduction. And when we say that we have a general reduction of I, we always mean an ideal like this J comma F to the D, always. And now the point, and this is the theorem that I want to point out, the big theorem here that gives us the interpretation of the core, answer question 1, is work first with Vitulio and Urch when we did it for the zero-dimensional ideal in early 2000, and then this is a preprint with Montagno and Fuli in the more general case that says, so if you have I that has GD, I already talked about GD last time. Obviously, if you have the zero-dimensional case, there are no conditions because these are all satisfied, as we said last time. So the minimal number of generator of IP is less than equal than the dimension of RP. Remember, this is JD for every P in V of I, but different from the maximal ideal. So you don't have any condition globally. And then the other condition, I'll put it, but I'll not really explain it, is a very mild condition, is asking that when you localize I at M is D minus 2 residually as 2. And I'm not going to explain what this is. I'm just going to tell you that, remember, last time I had a condition on the depth of the power of the ideal that much stronger than this one. And all the family of ideal that I showed you last time, the Licci with GD, all this ideal, the and primary ideal, the ideal that they are generically complete intersection in dimension 1, they all have this property, but many more ideal have this property. They're much lighter. This condition, the second condition, the first was mild anyway. I'll call them star again, but remember that these stars are essential for what I prove, because if you don't have either the first condition or the second condition, then we have counterexample. So this is not true. So the core of I, what we prove is that the core of I is the mono of K for any K general reduction of I. Okay? And now why is this theorem interesting? This theorem gives you a new interpretation of the core in terms of operation of monomial ideals. The core is the largest monomial ideal containing a general reduction of I. It also provides an algorithm that is more efficient than the formula, and then there is no restriction on the characteristic. Now, we already know that the core is contained in the mono, so we really have to show only the other inclusion. And how do you show this inclusion? What's the idea? Okay, so now I show the other inclusion, okay, and the other inclusion follows from a proposition that is actually true in any generality. It does not need this condition at all. So this proposition says, again, was proved first from PUV and then FMPU, that the mono of K does not depend the general reduction K. And this really is what proves the inclusion, because this is the real core of the thing, if you want, because once you have this, you get immediately the proof of the theorem. Why? But let me outline it here. But remember that this condition star, I did not put this condition last time, but were actually the condition that we needed in the local case with Corso and Ulrich to prove that the core is a finite intersection of general reduction. And that case were finite intersection of general minima reduction. But actually you can prove, and we did this with Fully and Montagno, that you can actually, and Ulrich, that you can actually condition star enough to write the core even for as intersection of finite general reduction for a K algebra. And now the fact that the mono of K is independent of K says that the mono of K is equal to the mono of Ki. So any K you're going to take has the same mono. And this mono are obviously containing Ki for every I, and then this immediately give you, if they are containing every Ki, they are containing the intersection. And then the mono of K is in the core. So really the crucial thing is here the proposition. And how would you prove this proposition? So this is actually the last thing I want to do for this section, and then I go to like segment ideal. So let me tell you how you prove this. Just the idea of how you prove it, because I think it's important and interesting. Then I want to go back to our example to actually show, maybe I go back now to the example first. Let's go back to the example, and then I give you an idea why you prove the proposition. So in our example, the ideal, if you remember, was x1 cube, x1, x2, and x2 square. Now, we always know that the adjoint of I square is contained in the core, and by what I said just now, is always contained in the mono. Actually, you have an equality in this case because it's a zero-dimensional ideal, but it doesn't matter. But it's contained in the mono of K for every K, actually. You don't even need general K, for every reduction. Okay? So I should even put J here because it's not a general that I talked before. I really want any reduction. And now, how can we compute the core in this case? But it's very easy because you compute the adjoint using NP0y, the Newton polyhedron, and you get that the adjoint is x1 to the fourth. It's very easy. You can do it if you're bored. x1 square, x2, x1, x2 square, and x2 to the third. Just as the formula I gave you before. And then you can choose a j and compute the mono of 1j. And the mono of j that we choose to compute is the mono of x1 cube minus 3x1 x2, x1 square plus x1 x2, and x2 to the fourth. This is a reduction. You see, is a combination of the generator of I, and then we throw something to I power. F to the d is our x2 fourth. And when you do the mono of this j, and you can check as a j just with a computer, you get exactly the same ideal here. This is equal to this. Sorry, wanted to take this. So the core is sandwiched in between these two ideals, which are equal, so the core has to be one of them. You could even compute the mono of the general reduction using Monzin ideal, and that would have done it, but I wanted to do it here in general for you. I also wanted to tell you before I prove the theorem, an example. I'll not analyze this example, but I tell you there is an easy example there are examples for when both conditions are not satisfied, and they're very easy to write. One is x1 cube, x1 square, x2, and x1, x3 square, x3 to the cube. This ideal is I2. It does not have G3. That's a problem. And then in this case, the core of I is not the mono of K for K general. And furthermore, this is even more important, the core is not the intersection, and that's why it fails. because the proposition works anyway. What it fails is that it's not intersection of finite, reduction, general reduction. It is the intersection of a finite number of reduction. It's another open problem because Jugal wanted as many open problems possible. That's a very difficult open problem, but with Bern-Ulrich, we always conjecture that the core for any Comecoli ring is the intersection of finite reduction, but we don't know how to find such reductions. So let me just give you now an idea of the proof of the proposition. Remember, the proposition states that the mono of K is independent of the general reduction. How do we prove the proposition? We take a ideal which looks like our K but is generic in the sense that we take not a linear combination of the generator of I, but we use variables. So these are the generators of I, the monomial generator of I. And we take variable, and obviously I had told you when we form K, we have to take D such combination, general combination. So we have to take of D of this generic. This ideal now, and then we throw the element Fd for any F different from 0 in I. So this B correspond to our K, and I would call it a generic reduction instead than the general, and is contained in this larger ring, polynomial ring, which I'll call S, okay? And now you can consider the homomorphism pi lambda that send S to R and send the Zij just to lambda ij, which are in K, in the field K. And now notice that if you do pi lambda, let me write it here, pi lambda of my beta, I exactly get my K for lambda general. And this is a general reduction. Like before, the K always indicate a general reduction of I. So for lambda general, I always get what I want. And now what we prove? We prove the following. First of all, we use again, and that's why I stressed it before, we use the algorithm of Strumfeld, Saito, Takayama, and we can define the mono of this strange ideal really is the mono respect to the X variable, because here you have lots of variables, so you have to tell which one you multi-homogenize respect to the X variable. So we think of the Z just like constant, and then we have to intersect with S, okay, and the Z are just constant. Remember, you add new variable U, each one for every X's, you multi-homogenize thinking that the Z are just constant, and then you contract back to your ring, but in this case is S. And this is our mono. Maybe I should put it in red because it's the definition of this object. And now what can we prove? We prove for lambda general that, and this is the crucial thing, the multi-homogenization of pi lambda of beta, now this is going to be the multi-homogenization already in the ring R, okay, there is no Z anymore, is equal if you first multi-homogenize beta and then you apply pi lambda. And this is very important because it immediately gives you, because of the algorithm, that the mono of pi lambda of beta, which is exactly, remember, the mono of my K, the object I want, okay? This guy is pi lambda of mono of beta. And why do I care about this? Because it's easy to prove, actually, that pi lambda of mono beta does not depend on lambda for general lambda. Remember, lambda is general. Why is this be so clear? Because the mono of beta is generated by monomial in the X's, with coefficients that are polynomial in the z's. And as long as we make sure that this polynomial, the coefficient do not vanish, and this is an open condition, we always get the same monomial ideal. So that B is easy. A is the difficult thing to prove. And then you get that the mon of K is independent. This is the large K, don't confuse it with the field, is independent on this general reduction K. Okay, so now I would like to go to the last part of my talk. I don't have much time, but I still, since I started a little late, I have 10 minutes. Maybe this is enough, but at least I would like to point out something, because there is an open question here and I would like people to think about it. And that's what Jugal wanted me to give you, as many open questions as possible. So I want to talk about like segment ideals. So remember, first I've redefined it for you in case you don't remember what they are. This RT is the K vector space spanned by monomials of degree T. And then you take any, I'll call it, since it's any, I call it always L, any homogeneous ideal of R, and you let IT be the subspace of RT, okay, so they are of degree T, generated by the largest, this is important, okay, and how many? HLT. HLT is the Hilbert function of L in degree T, monomials in the lexicographic order, with, that's why it's called X, X1 bigger than X2, bigger than XT. And then you set I to be this ideal. Actually, it's not an ideal in theory, but it turns out to be an ideal, and it's called a Lex segment ideal. And it has the same Hilbert function of L, and it has is the largest ideal with actually the same Hilbert function and the largest Petty number. I mean, it has a lot of beautiful properties, and is very widely studied. Now, the proposition of that we can prove, we prove with Full and Montagno that Lex segment ideal that have L equal D, okay, have property star. So they all have property star. And then we prove actually that the Lex segment ideal generated in the same degree T, which is bigger than equal than 2, then they always have L equal D. So practically, as soon as you assume that the Lex segment ideal is generating the same degree, then you immediately get all conditions that I put in the proposition. So this tell you, let's look at the family of Lex segment ideals generated in degree T, with T at least 2. And let's take our I now, not just a monomial ideal, but inside this family. Then, by the theorem I point out before, the core of I is the mon of K for K, a general reduction of I. And now the conjecture, and that's the open problem that I want to put here, and I'll tell you the progress we have done towards that. The conjecture is that the core of I is actually simply I times a power of the maximal ideal. And which power? The power is a little difficult, I write it, but is D times T minus 2 plus G minus T plus 1, where G is the height of the ideal, T is the degree of the generator, and D is the dimension of the ring, okay? And now, what can we prove of this conjecture? But first of all, we can prove what usually is the difficult inclusion. We can prove that the core contains this ideal. How do we do that? This is a very nice proof, so I want to outline it. The thing is this: since the core is equal to mono, so I'm using this thing, okay, to prove this inclusion, it's enough to prove that this huge power of the maximal ideal, takes me forever to write it, is contained in K colon I. Why? Because obviously this would tell you that I multiplies this power inside K for this K general reduction, but if it's inside K, since this I times this power is monomial, is inside the mono K, so it's inside the core, and you're done. So really, this is enough, it's enough to show this, but this thing is a d-residual intersection of I. And this is important because then to prove in general this, independent of being a d-residual intersection, to prove this inclusion, it's enough to prove that the Hilbert function of this ideal in this degree is zero, obviously. And now, by local duality, this is the same as proving that the initial degree of the canonical module of this guys is at least this number minus this number. And now, how do we prove this? But because this is a d-residual intersection, we have to prove something about the initial degree of the canonical module of this d-residual intersection. And using actual result of Chardin and Eisenbach-Ulrich, we actually prove a lemma that shows that the initial degree of the canonical module of this residual intersection can be bounded as long as we can bound actually the initial degree of some d-1 residual intersection or every d-1 residual intersection, and we do that by induction. Okay, I'm almost done with the talk and my time is almost off. I would like to talk about the open problem, which is the other inclusion. And I want to point out that it's enough to show that x1 to the d times t minus 2 plus g is not in J, and now I don't put K, I put J for some. So it's enough that you find a reduction of I for which this power of x1 is not in J, but we could not do that. Why it's enough? It's enough because I is generated in degree T. So because generated in degree T, I intersect that power of the maximal ideal, this power, T minus 2 plus G plus 1, gives you actually the product that you want. However, okay, so to prove that the core of I is in this product, since the core is here, it's enough to prove that the core is here. So it's enough to show that the core is in this power of the maximal ideal. But Lex segment ideal are strongly stable, and the core of strongly stable ideal is strongly stable. So to prove that the core is in this power, it's enough to show that the power of x1, the previous power of x1, is not in the core. And to show it's not in the core, it's enough to find one reduction where that power is not in. Now, we could not do that in general. We could, in characteristic 0, the theorem is known for T equal 2 by Bonnie Smith. She was my student. Actually, she was the first one that did this kind of thing. And then we could prove it with the Fuli and Montagno and Ulrich if the dimension of the ring is less than equal than 1. Okay, and this finished my talk just on time, and I would like to thank everybody for the attention. Are there any questions?
Yes, people can unmute and ask questions.
Jugal, I have a
Yeah.
question. Marilina.
Yes, yes.
This is my curiosity, but Claudia,
Yes,
if you assume take any, for instance, a primary idea,
yes,
assume that you have information on the reduction number
yes,
about then the maximum of the reduction number. For instance, take that is very small, two, maybe one is clear, but the reduction number is two. Can you say something about the core?
yes. You can say a little more, at least in these cases. You can, and these are actually being done by my students. For example, in the monomial case, Angela Colaus could say more about when the core is the adjoint. If she has a small reduction number, exactly reduction number 2, she consider that case, and then you can have more information. Yes, Marilina, you can. Remember, even in the primary ideal, where reduction number 2 is not expected reduction number, because remember last time I show a theorem, but if you had the expected reduction number, then we knew exactly what the core was just that formula, j I to the reduction number plus 1 colon j. Remember that formula here?
Yeah.
Yes. And if, which is this one, no? Now, so sorry. Yes, colon j to the n. Now, if the no, it's the other way around. Sorry, what
This
did
is,
I write? Jn plus 1 colon I to the n.
yes.
But the point is that if this is the correct formula, sorry. Now, if if the reduction number is 1, because you're talking about the primary ideal, and actually becomes much easier in that case, because if the reduction number is 1, remember we talked about it, is j times j colon I, so it's very easy. However, if the reduction number is 2, this is not true in general, but for the monomial case, she could prove that when the core is the adjoint, you just have to check, you know, some other, I don't remember the condition, but some other minor condition to actually check that the core is the adjoint. I think the core has to be obviously integrally closed, but you don't need anymore this this thing to have a monomial reduction. Remember, I mean, she has this assumption, which is very strong for her theorem, that it has to be a monomial reduction. But you don't need that anymore. You understand?
But only in the monomial case.
In the monomial case. In the general case, I don't think for small reduction number, I don't think we really studied so much. So that would be an interesting thing. What is the core for small reduction number? Obviously, you're asking the primary case, we know it anyway, because in primary case, the formula I wrote is true in general. Remember, that's the formula that we prove with Ulrich, because the formula in the primary case, the core is always, it would always be j squared colon I. I mean, the reduction number you told me was 2. So it's always this, in any case. That's a formula that we prove with Ulrich, but it's also the formula for the primary case was already proved before by Irian Smith and by Unick and Chung. We proved it with condition star, but condition and primary, these are always satisfied. So we'll always know the core is this. The question is the core of the adjoint? That's why I went back to the adjoint.
I understand.
Because this one we know the shape of the core. If in the primary case, we know what the core is. I mean, the primary case, that's not a problem. It's really the problem how to describe it, not just using the formula where we know in the primary case, but having another description, that is easier than the formula, because the formula we have in the primary case.
I understand. Thank you, Claudia.
Yeah. Claudia, I have a question. You mentioned that if you take monomial ideal in polynomial ring,
Yes.
which is asymptotically normal, then because Rees ring has rational singularities, core of I is adjoint of dth power of I.
Yes.
So I'm wondering if this is true in more general rings, like suppose you take just a regular local ring. and take a ideal M primary ideal.
Yes.
Which is normal M primary ideal in regular local ring, and take Rees ring. Suppose it has rational singularity, whether the same formula holds.
When it holds, if it has rational singularity, that's the color I wrote last time. Yeah, that's the one I wrote last time, Jugal. That if you have if the proj of the Rees ring has rational singularity, then we know the core is the adjoint. The problem is that, that's what I tried to say at the end last time. The problem is that if you know that the Rees ring is normal and come coli, but does not have rational singularity, then the core, it cannot be the adjoint by the work of Hubel. Because Hubel showed that if you know that the Rees ring is normal and come coli, for the core to be the adjoint is if and all if the proj of the Rees ring has rational singularity. If and all if. So it's needed. However, in this case, in the monomial case, this is not an obstruction, because if you have normality, you automatically have rational singularity because of Oxter and Buteau. That's why we look at the monomial case. There, we don't need to have rational singularity because normality gives you rational singularity. So we are looking really for conditions that are weaker than normality, and try to see that in condition weaker than normality, we can actually get the core the adjoint. And this is the whole point, to try to do it with condition weaker. And that's actually the, if you want, conjecture, I would call it question of Craig. In the monomial case, if this, which is much less, gives you, R1 just give you the core being the adjoint. And as I said, this is known not just in the monomial case, is known also for ideal generated by the same degree, but in two variable by the work with Kasten and Ulrich. But I think it's true more in general for family of ideals. For family of ideals where you don't have the obstruction of Hubel. So as soon as you don't have that obstruction, so as soon as you know that normality and common-coldness would give you rational singularity for the Rees ring, then I think R1 should be enough. That's my feeling.
Okay, thank you.
This is Jayantan. I have a question. See, when we take square-free monomial ideals,
Yes.
like it has a lot of combinatorics and topology. So in those cases, do we have some, some nice structure on the core? Is it known?
I would say that I don't know. I don't know if people have worked on it, but I don't think so. The core was worked out for some, the core of square-free monomial ideal was worked out in the case of generating degree 2. So when they correspond to graphs, by Mori and Ulrich, and by Mori and Fuli, and they have a nice combinatorial description of the core with some assumption, but they have some assumption. In fact, that's one case where we know that the core is not the mono, and our formula does not work because we don't have this residual condition. I think it's something like an hexagon. So you take, the edge ideal, which is the edge ideal of an hexagon. 1, 2, 3, 4, 5, 6. And then you take, I think, whisker. I think this one, if he has at least 2 whisker, I believe, that's a case that it has GD, but it doesn't have the other condition I put up, this residual condition. And then the core is not the mono. We still could compute the core in this case, but the core is not the mono of a general reduction. The core is still a finite intersection, but you have to find a special reduction, and we're able to find them in that case, but it's not the mono.
Okay. Thank you. I have one more question in the leg segment part. Like, if it's not generated in like single
the same
degree.
Yeah.
Yeah.
We did not really do that case. You could assume just that L is equal D. And even in that case, ask what's happened. I mean, remember, the inclusion of the core is still true. I think for that we don't need form of the same degree. For one inclusion, we have it anyway. So this formula will still be, no, we need form of the same degree, even in that case, because we need to know that it's generating degree D. So I would say that, no, I don't know. I don't know in that case. If it's not generating the same degree, I don't know.
Okay.
You still would have, because remember, if you assume L equal D, which is not a big assumption, you still would have the property star. So you will still know that the core is the mono. That you'll know, because this doesn't need form of the same degree, this part.
Yeah.
But then you have to, you have to guess a formula like this for the core in that case.
Yeah. Okay, thank you.
Okay.
All right. I don't see any further questions. Yeah. So, Claudia, on behalf of all participants, let me thank you for your very nice talks and giving